Hello everyone, today yours class number 37. Class number 37 for EMFT. Okay. So today I will start the time varying field. Okay. Today I will start the time varying field. So what is time varying field? So time varying field is nothing but when a vector field is depending on the time, that is the vector field results some parameters with respect of time. That means as the time is elapsed, some parameters changing its values. Okay, as well as in every equation of this chapter there is a factor which is time is being used in every cases. Okay, so your first topic is the very much important topic in your exam purpose. It is very much important, right? The Faraday law. Okay, so first right Faraday law, first topic, Faraday law. Okay, so Faraday law states that, right, the EMF induced in a closed circuit, is proportional to the rate of change of the magnetic flux linkage and the direction of the current flow in the closed circuit, is such that it opposes the change of the electric flux. That means the EMF induced in a closed circuit is proportional with the rate of change of magnetic flux linkage. That means what? The EMF whatever induced is directly proportional with rate of change of magnetic flux within it. Okay, and the direction of the magnetic flux linkage and the direction of the current flow in the closed circuit is such that it opposes the change of flux. That means the direction of this, if we consider the direction, then E is proportional to minus d phi dt. Okay, and if we consider a constant, then the constant will be nothing but your number of turns. The constant is the number of turns. Okay, this is your ultimate formula for your Faraday law. According to the definition, we can found this type of these two statements, and after that we can conclude it as a constant n equals to number of turns present. Okay, so next, right, the minus sign, the significance of the minus sign we have to discuss. The minus sign is an indicating that the EMF is in such a direction as to produce a current whose flux is added to that original flux, would reduce the magnitude of the EMF. That means whatever the flux is induced due to this intensity, due to this electric flux, or due to this EMF, will be oppose the actual flux generated by the current. Okay, generated by the current. That means, again I repeat, the minus sign is an indication that the EMF is in such a direction. This EMF is in such a direction as to produce a current. So this EMF will produce a current whose flux is added to the original flux, whose flux would added to the original flux would reduce the magnitude of the EMF, would reduce the magnitude of this EMF. That means this EMF will reduce by itself by producing another flux which is in opposite direction to the original flux. That means suppose a original flux is flowing through here, and due to this original flux change there will be a EMF E. Okay, and due to this EMF E, again another flux will be produced. Suppose this is phi dash, which is your which results a decrement of phi minus phi dash. Okay, again now it will become phi 1 now, so U will be reduced, so U will now become E1, and this due to this E1 and due to this phi 1, suppose E2, suppose this E1 will be produced. Okay, due to this phi 1, E1 will be produced, and this E1 is also produced another flux phi double dash, and this phi double dash again decrease this phi 1 by some value phi 2. That means to some value phi 2, having a equation this one. Okay, so by this way it is gradually decreasing. Whatever the flux, once it is flux is linkage to any particular system, and it will produce an EMF, and then it will gradually decreasing. until or unless continuous supply of the electric current is present. Okay, then write this statement, then write continuously this statement, the above statement whatever I am telling by note basis. This statement that the induced voltage acts to produce an opposition flux is known as Lentz's law. So this is actually the Faraday law, and this statement is actually from Lentz's law. Okay, so actually Faraday law and Lentz's law are combined to form a complete equation. Okay, so Faraday, you can also write Faraday law and Lentz's law. Okay, Faraday law and Lentz's law. Okay, you can also modify the heading first. Okay, so then write this, the EMF is obviously a scalar quantity. Always remember that this EMF, whatever the EMF is induced, is obviously a scalar quantity. Okay, and a dimensional check shows it is measured in volume. So if we dimensionally check it, then it will measured in volume. So EMF will be in volts. Sorry, EMF will be in volts. Okay, in volts. So we define the EMF as, so we can define the EMF as it is a volt, so we can treat it as a voltage, right? So EMF can be defined as, EMF can be, whatever the EMF is induced can be defined as closed line integration of E dot dl, intensity dot dl, or this EMF, yes, this EMF is a scalar, okay, and it is a vector because it is a intensity. It is a intensity, and this is the EMF induced. Okay, you can modify it by using a E dash. So E dash is intensity over here. Okay, whatever the E dash I have written here, which will be taken as intensity. Okay, so this is the voltage about a specific, right? This is the voltage about a specific closed path. So for a specific closed path, it can produce a voltage. Okay, and if any part of the path is changed, generally EMF changes. So if any part of the path will change, then the EMF is also changing. Okay, so can you write it? This EMF E equals to minus ddt of integration B dot ds, right? We can easily write it. So if we now we are taking it as a double integration. Okay, so what will be your expression? See, ddt of b ds, that will be, you are taking del b del s. It is the property of any differentiation or integration, that is calculus. Properties of any calculus. If any ddt term will get inside the double integration, then it will be partially differentiate. It will become the partial differentiation. Okay, so this is E equals to minus double integration dB dt of over ds. Okay, so now we are applying the Stokes theorem here. So if we apply the Stokes theorem, then what happened? The surface integration. So surface integration of any this vector, which will be equals to what? Which will be equals to surface integration of curl of E over ds, because this is your EMF. Okay, so from here you can find this one. Okay, so from here you can find this one, and this EMF is also will be equal. So these two equations are also equal, right? So actually what happened, we are taking a closed line. Okay, this we are taking a closed line from A to B. Okay, so this line is nothing but closed line integration of dl. Okay, and if we consider the intensity E first, then your integration will be E dot dl, right? So which will produce the total EMF, okay, which will produce the total EMF. Now we are taking the inside part, that is we are expressing the intensity for this equation, by this equation. Okay, ddt of b ds, and which will be equals to this one. And similarly EMF can also be written in this form by applying Stokes theorem. Actually we are applying the Stokes theorem over here, from here to here. Okay, so you can put a equation number 1 and apply the Stokes theorem in equation 1. Apply the Stokes theorem in equation 1. Okay, so this E dot dl can line close the integration can also be expressed in the surface integration in which is enclosed by this line, right? This was the Stokes theorem. Now we can easily equate this equation with that equation, and whatever your result, your answer will be, after equating this, your answer will be curl of E equals to minus del B del T. Okay, minus del B del B. Previously it was curl of E equals to 0, and now it was curl of E equals to minus del B del T. Okay, this is your modified, right? This is the modified Maxwell's equation for time varying field. This equation is a modified Maxwell's equation for time varying field. Okay, so write when B equals to constant, then del B del T equals to 0, and that condition the electrostatic field will be produces a 0 vector, right? So that means it will produce E rotational. So when for a time varying field, when the B is constant, then only the curl of E will be 0. Okay, so until the V is not a constant with respect of time, then it will shows this type of result. Okay, so actually I am telling again in a complete line. So you have to first find the EMF by using this basic theorem. This is the intensity. Okay, and by applying the Stokes theorem we can write this curl of E ds. Okay, just again I repeat it in very fast. Okay, so this is your EMF, and again now EMF can be expressed in case of your inside part, so it will be B dot ds, right? So if we taking inside it, then it will become del B del T over ds. Okay, so now we are integrating these two equations. So by equating these two equations, we have curl of E over ds equals to integration of del B del T ds. Okay, now cancel out, then from both sides the surface integration, it will become this equation. Okay, so I am telling again in very fast. Okay, so just write it. This is your Faraday law expression. Okay, so what is the Faraday law? If there is a question in your exam, then you have to write, you have to find the up to this much. Okay, by applying this one and up to this much. Okay, so this is your Maxwell modified Maxwell's equation. This is a modified Maxwell's equation for time varying field. Okay, so next topic, induced EMF for different cases. So induced EMF for the different cases of time varying field. Okay, so right, according to the Faraday law, there are three possibilities by which the EMF can be induced. Okay, so right, first one, by having a stationary loop in a time varying field. By having a stationary loop in a time varying field. Okay, and second one, by having a time varying loop in a static magnetic field. By having a time varying field in a static magnetic field, and third one, the last one, by having a time varying loop in a time varying magnetic field. By having a time varying field in a time varying magnetic field. So time varying, it will be magnetic field, right? Magnetic field. That means for production of EMF you have to vary with respect of time, either loop or the your time varying field, or that means magnetic field. So you have to move the loop by some velocity, or you have to change the magnetic flux with respect of time. Okay, so first write, so first application. So do this heading first, then write this EMF induced by the time varying current, this EMF induced by the time varying current, within bracket write, producing a time varying magnetic field. So this EMF induced by a time varying current, that means a current when the current is varying with respect of time. Okay, in a stationary loop is called transformer EMF. Is called transformer EMF because in this transformer this type of EMF will be generated. That means a stationary loop is present. In case of transformer, what? There will be a core, right? So there will be a stationary conductor. There is no rotational part. Only the time varying magnetic field, whatever the magnetic field is producing here, it will be moving with a with respect of time. That is, time varying magnetic field will induced over here, and by introducing these two, you will get a EMF, right? You will get a EMF. So similarly here also you can write. So secondary case, the fields, the loops are static, and the flux are moving. So that's why flux will produce this the static conductors will produce a EMF V2. Okay, so this is your transformer EMF, and the expression will be curl of E, whatever the last time I have discussed, that is for the Faraday law, del B del T. Okay, this is your ultimate expression for the first one. Okay, so now I will move into the second case. So let's remember, this EMF is called the transformer EMF. This is called transformer EMF. Okay, and now second one. So do this setting. So time varying field in a static magnetic field. Now here is a magnetic field will be static. So right, when a charge is moving in the presence of a static magnetic field B vector. So when a charge is moving in a static magnetic field B vector, then the force on the charge will be equals to what? Q V cross B. Okay, this formula already I have been discussed. Okay, so make it equation number 1. So where Q is the what? Q is the amount of charge, and V is the velocity of the movement of the charge. This is the velocity of the charge. This is the amount of charge, and B is the uniform magnetic field. Okay, this V is the uniform magnetic field. So now write, so we can define the motional electric field. So we can define, now this is a magnetic field, magnetic force. Okay, so we can define the motional electric field EM equals to this FM by Q, right? This is called motional electric field. So this will be V cross B, right? V cross B. Okay, thus if a conducting loop is moving, so what is the significance of it? When a conducting loop is moving with a velocity V vector inside a magnetic field, that means what? In case of your motoring principle, a conductor was there, armature conductor. Okay, so this armature conductor is moving with a velocity inside your magnetic field, right? Inside your magnetic field, right? So this case, magnetic field is moving, but magnetic field is constant. That is, magnetic field is constant means magnetic field is uniform, phi equals to constant. Okay, and your armature conductors are moving, or the loops are moving. Okay, so that's why the EMF will be equals to what? Close the integration of this EM into dl, right? EM into dl. That means so it will be equals to what? EM will be equals to this one. So close the integration of V cross B. Close the integration of V cross B into dl. Okay. So by applying the Stokes theorem, now I apply the Stokes theorem. So what is the Stokes theorem? Surface integration of curl of EM. So in the left hand side we are integrating. So it will be equals to here also we are integrating the curl of V cross B, Stokes theorem. Applying the Stokes theorem. That means the left hand side we have applied over here, and the right hand side which will be equals to this one, which will be can again applied the Stokes theorem here. So application of the Stokes theorem here from the both side. Okay, we will get the ultimate result this one. Okay, so now ignoring the integration, so it will becomes curl of EM equals to curl of V cross B. Okay, curl of V cross B. So right, this is called the motional EMF. This is called, so this term is called motional EMF. So E motion, you can write motion. This is called motional EMF. Okay, or flux or flux cutting EMF. Motional EMF, or another name is flux cutting EMF. Okay, as found in electrical machines, motor or generator. Electrical machines, as found in rotating machine of electrical. Okay, so the last application. Now the last application, this is the third case, the time varying field in case of time varying conductor. That means like, right, if the magnetic flux density is also changing with respect of time, if phi not equals to constant, that is phi is changing with respect of time, with respect to time, and your B, that is phi or B, you can write also B is also not equals to constant, and the conductor having a velocity not equals to 0, that is velocity of the conductor not equals to 0. Okay, then write, then the transformer EMF and the motional EMF both will be present. Then the transformer EMF and the motional EMF both will be present. Okay, then the EMF equals to closed line integration of E dot dl, whatever the basic equation, which will be equals to surface integration of del B del T with negative sign ds vector, del B del T with negative sign ds vector, so B will be taking as vector wire, plus closed line integration V cross B over, or closed surface integration V cross B, or you can say closed line integration first, V cross B dl vector. Okay, so it will be your ultimate equation, because here we are taking, so this EMF will have two components. This is your transformer component and this is your motional component. Okay, so so what will be your result? So this one will represents what? This one represents, so if we apply the Stokes theorem over here, then it will becomes surface integration of curl of E over ds, which is enclosed by this closed line, which will be equals to curl minus del B del T over ds vector, plus double integration of curl of V cross B over ds, right? So if we cancel out, then from the both side it will become what? Curl of E will be equals to, it will have two component, del B del T plus curl of V cross B, right? So this will your ultimate expression for this third case. That means when motional EMF and transformer EMF both is present for a system. Actually this function is this is actually the practical system. Okay, this is actually the practical system which has both transformer EMF as well as the motional EMF. Okay, so this is your transformer EMF, this is your motional EMF concept. Okay, so today's class up to this much. Wait for next day, I will start the next topics of this module, that is your displacement current and your Maxwell's equation. Okay, so thank you.